Hello and welcome to today's lesson. My name is Mr. Johnson. This is one of my 20-minute lessons, and I am going to talk to you today about half-life. This is part of the physics radioactivity unit, and yeah, I'm just going to share my screen with you now and get started. One moment. Okay, you should be able to see my screen now. And like I said, this is one of our lessons on the GCSE physics topic for radioactivity, and let's get started. So by the end of this, what you should be able to do is understand half-life of different radioactive sources and its implications for storage and usage of those sources. Starting off with how we can describe how radioactivity of a substance changes over time and recall the unit that we use for radioactive count. So radioactive decay is a random process. That means that we can't predict when it will happen. Sometimes when you throw a die, you get a 6, sometimes you don't. The probability of getting a 6 then is 1/6 or 1/6. In a similar way, at any given moment, there's a certain probability that a particular unstable nucleus will decay. As you can see from our clock and our atoms on the side in the GIF, as they're going through, there's no particular pattern to which red atom turns green. They're randomly decaying, but we can give a particular probability that the unstable nucleus will decay. When an unstable nucleus undergoes radioactive decay, its nucleus does change to become more stable. We've encountered this before. The activity then of any radioactive substance is literally the number of nuclear decays every second, and it's measured in a unit called becquerel, BQ for short. 1 becquerel is 1 nuclear decay every second, so it's 1 nuclei decaying to become more stable every second. As an idea of this, a sample of uranium-235 has a decay rate of 2 becquerels. How many nuclei decay each second? And the answer with 1 becquerel is 1 decay per second. 2 would be 2 decay per second. 100 becquerels would be 100 decaying per second. If you like, it's a measurement of the frequency because it's the number of decays per second. So taking a look at this then, just to recap what we started with, radioactive decay is then a random process. We cannot predict when a particular unstable atom will decay. If we have a large enough sample of atoms, we can predict approximately how many will decay in a given time. The number of decays in a second is the activity, and it's measured in becquerels or BQ. As an unstable atoms decay, there are fewer of those left to decay, and so the activity decreases. Okay, that's our first point there. Describe how radioactivity substance changes over time, recalling its unit. Next point. Describe the half-life of a radioactive substance as a change in its activity by half the original value. Half-life then of any sample is the time it takes for the total number of radioactive atoms present in a sample to decrease by half. Textbook definition. Half-life is the time it takes for number of radioactive atoms to decrease by half in a sample. This is a good idea or a good approximation of it from a diagram where we have 16 green atoms, which are representative of an unstable nucleus. And then after one half-life, half of those have decayed into the red decayed nuclei. So we've got 8 red, 8 green. You can see now we've got fewer left of the unstable nuclei. So now we've got a lower count rate. And this can be plotted as we're going along on a graph of activity in becquerels against time. After another half-life, we have fewer again. After another, fewer again. And so the activity rate drops and we get this particular pattern, this, I like to call it a sideways smile. And as you can see from the graph, from activity across the time, it keeps on decreasing like so, but it never ever quite touches zero. There have been questions about this before where they give you the graph axes and ask you to plot what the graph of a half-life for any radioactive sample would be. And the idea is that it decreases as a smooth curve, but it never quite touches the x-axis because there's always a small amount of decay and radioactive nuclei present. The half-life is the same for any mass of an isotope. if we're talking about the same isotope every time, it doesn't matter if I've got 50 grams, 100 grams, 10 kilograms, 1,000 kilograms, the half-life of it would be the same. The only difference now is I've got more of those nuclei present. This is only true when I'm talking about the same isotope. So to clarify, let's say I have 1 kilogram of uranium-235, which is radioactive. Its half-life would be the same as 50 kilograms of uranium-235. The element is the same, doesn't matter about the mass, so the half-life remains the same. However, it can change if I pick a different element. For example, radon gas has a half-life of 3.8 days. Some elements can have very short half-lives. Some radioactive elements can decay very quickly. Some have ones that can last for millions of years. As an example, I've put a table here, and you can see the differences. So uranium-235 has a half-life of 700 million years. That means that in 700 million years, if I started off with 100 atoms, after that 700 million year time frame, I'd have 50 left that were radioactive still. So it takes a long time for U-235 to decay. Carbon-14, which is a radioactive isotope of carbon, is 5,730 years. We actually use this one in the process of carbon dating ancient remains and ancient finds to see how old they are. Cesium-137, half-life of 30 years. Radon-222, 3.8 days. So you can see that the radioactive half-lives vary quite considerably depending on the isotope that's being discussed. Now, like we said before, we cannot say which nuclei in the sample will decay next. What we can say is that the activity or the count decreases each time an unstable atom decays and then becomes stable. This means that over time, a radioactive sample will become less radioactive. Here we've got a diagram representing the number of atoms that are there. But this then leads to another definition of our half-life. Because if we're also saying half-life is the time it takes for the number of radioactive atoms to decay by half, then half-life is also the same as the time taken for the radioactive decay count to half, because that's the measurement of how many radioactive atoms are left. So both those definitions work. So if we take a look at this now, what's the half-life of the the atoms in the sample above, and how can we find out? Now we can see that roughly every 4 seconds, every 4 seconds, the number of radioactive atoms in the sample is halving. This means that it's halving every 4 seconds, so the half-life of the sample is 4 seconds. This is one of the things that you have to be able to do, is to calculate half-lives based on what you know about the atom from the question that you're given, or the radioactive isotope from the question that you're given. You have to use both graphs and maths to help calculate the half-life of a sample. So let's start off with a graph, and I've got an example here. In figure D, the activity at 3 minutes is 800 counts per second. After one half-life, the count rate will have decreased to 400 counts per second. This occurs at 9.5 minutes, so the half-life is 9.5 minus 3, which is 6.5 minutes. Now, I always say to my classes and the pupils in my class that in questions like this, my ruler is my best friend. Because what I do is I would look at one half-life and I draw a line on. So I've started at 800, and then that line there at 400 is half of 800. I draw along to where it intercepts the curve, and then draw down to where it intercepts the time axis, and then read the difference between the two. To make this a bit clearer, I've got a nice straightforward graph here. I find the number of counts at a time to start. In this case, I'm going to use time equals 0 because it starts at 80 and I can easily find 40 on my axes, which is half. At time 0, counts equals 80. Find half the number of counts. 80 divided by 2 is 40. Draw a line at your half count rate. Where it hits the curve, draw a line from the y-axis to intercept it. The difference in the time is the half-life of the sample. So you can see From my first intercept at 0 to my second at 2, the difference in time is 2 days. If I were to extend this further and draw a line at 20 and intercept the axis and bring it down, it would come to 4. But the difference between 40 and 20 is the difference in days 2 to 4, so it still remains the same half-life, 2 days. So if we take a look at a graph like this, there are 2 radioactive sources decaying at different rates. This means that one source must have a different half-life to the other. Source A is represented by the blue dots, source B by the red squares. Question here is which source has the longest half-life, and how can you tell from the graph? 9 times out of 10, this is the kind of question that comes up in an exam where they say to you, use evidence from the graph to support your answer. First off, if we take a look, we can use the ideas that we've just used with a ruler and a pencil, and we can draw lines from a point where we can half easily. So for my red line, source B, I would go from 100, draw a line across from the activity and then down, and it would meet a time of 5 seconds. Half of that time is 50, so I'd draw another line across and down to 25 seconds. The difference there would be 20 seconds. That's the half-life of source B. Do the same thing for source A, only this time I'm going to start with a line at 0 and 120 and 60 to 5. And we can see that source B, the blue line, has a much quicker or shorter half-life, much quicker rate of decay. But we can also just talk about the fact that the steeper line, or the steeper rate of decay for the blue line, means that it has a shorter half-life because its activity is dropping faster because it's dropping in a shorter period of time. So here, either the line for source B is shallower or less steep. That's an argument that we can use, meaning that the rate of change in activity is slower. Or we can say that the time taken for source A to decrease in activity from 120 to 60 is 5 seconds, but for source B it's 20 seconds, so it takes longer to decay. And that's our second point. Describe the half-life of a radioactive substance as it changes, the half-life of radioactive substance as a change in its activity by half the original value. Last bit. Explain and demonstrate how it can be used to work out how much of a substance has decayed via calculation. If sample A started with radioactive 10 atoms, how many would be left after 5 seconds or 10 seconds? Now, because we've done this question earlier, we know that the half-life for source A, the blue line, is 5 seconds, and for source B, the red line, is 20 seconds. Sample A is source A. After 5 seconds, it would have undergone 1 half-life. So if it started with 10 atoms, 10 divided by 2 for 1/2 is 5. So after 5 seconds, it would have 5 atoms left. 10 seconds, well, that's 2 half-lives because it's 5 times 2. So the sample undergoes a halving of its original number of atoms twice. So for part B, I would start with 10 and half it to 5. And then for the second half-life, half 5 to 2.5. And that would give me my final answer. After 10 seconds, it would have 2.5 atoms left. It doesn't matter that I'm using decimals, I'm talking about 2.5. It is half of 5, so that answer is correct anyway. If sample B started with 100 radioactive atoms, how many would be left after 1 half-life? Now sample B, the red line, source B, that had a half-life of 20 seconds. So after 20 seconds, 1 half-life, if it started with 100, it'd have 50 left. But for part B, 4 half-lives, well, we have to half it 4 times, starting with 100. So 100 divided by half would be 50. 50 divided by half would be 25. 25 divided by half would be 12.5. And 12.5 divided by half would be 6.75. And that would be our final answer. So one way to lay it out is to take a look at it this way. Sample A has a half-life of 5 seconds. Every 5 seconds, the number of atoms decreases by half. So for the start, there are 10 atoms. Time, 0, number of atoms, 10. 5 seconds, 5, 10 seconds, 2.5. This means that after 1 half-life, 5 radioactive atoms, and 2.5 left after 10. That answers our first question. But notice how I've broken it down in almost like a table format, where I just literally write 0 is at 10, 5, 5, 10, 2.5. You always need to start with time 0, which is the original sample count before any half-lives have started. This avoids you missing a half-life or making a mistake by 1 half-life. For part B, sample B is a half-life of 20 seconds. At the start, we have 100 radioactive atoms. And once again, I've laid it out as a simple table. 0, number of half-lives 0, number of atoms 100. And then for every half-life, I've wrote the time that is taken down and got down to our final answer. So how does this look in practice? Well, that was that one there. 10 million atoms in a sample of radon-222. How many undecayed nuclei are left after a particular time period? Now, if you're given a question like this, they have to give you some idea of what the half-life is if they're asking you to calculate how many are left. But sometimes they can give you how many are left and a time period and ask you to calculate the half-life, in which case you're doing it in reverse. But to start with, half-life is 3.8 days. So one half-life, 10 million divided by 2 is 5 million. So that would be one half-life. What's left? 2 half-lives, 10 million divided by 2 is 5 million. And then divide that by 2 again, we get 2.5 million. So that's how much is left after 2 half-lives. 3 half-lives, we carry on. So 2.5 million is halved again to get 1.25 million. And then D, after half a half-life, half the amount would decay from one half-life. Or instead of 5 million decaying, it would be 2.5 million decaying. So there should be 7.5 million undecayed nuclei left after one half-life. And that is the end of today's lesson. So I hope you enjoyed that, and thank you for your time, and hope to see you again. Thank you for now.